Okay, so it's my pleasure to introduce Stephanie Gill. She's with CS in Harvard. I've been knowing Stephanie for a long time, not such a long time, but for some time, and even since she was a grad student at MIT. And then I think she had a real job for a little while, and then she was with Arizona State, and then she moved to Harvard 3 or 4 years ago. So Stephanie's general work is in multi-agent system, multi-robot systems. From what I remember, mostly issues related to trust and security. And Stephanie is very accomplished. I think she got basically everything that anybody could got at this stage in her career. She got the, let me think, NSF career. She just got the DARPA YIP and the ONR. Did you get the FOSR?
No, not FOSR.
Oh, why not? Okay, so today she's gonna talk about some recent work that I'm actually not very familiar with. So thanks, Stephanie.
Yeah, it is the resilient multi-agent work. So there is some stuff that Colleen is familiar with, but the newest part of what we're working on there. Okay, so thanks for the invitation. It's really great to be here to spend the day with you guys and learn about all of your research. That has been a lot of fun so far. Okay, so I'll tell you a little bit more about some of the work that we are doing in my lab. And so in a lot of the work that we do and what we think about often is the multi-robot network. And so multi-robot network, specifically, we look at two challenges. We want to know what happens when we put these systems out into the real world. And so specifically, we look at how can these systems deal with unknown information, so high levels of uncertainty that might be present in the real world, like partial observability, for example, and also adversarial action. So when these agents are out in the real world, they're using information to base their decisions. But that information can be corrupted or even intentionally manipulated by adversaries. And so we're very interested in these problems and understanding what happens to the coordination under these two kind of extreme cases. And the reason is because we want to see these multi-robot systems out in the real world. And in order for that to happen, we think we need to know how to deal with these two extreme cases. And so sometimes people, I myself, if I wasn't involved in this, I might think, well, robots and security, why do we need to think about that? But you should think of robots as cyber-physical systems. And so more broadly, robots are autonomous vehicles that are going to be on our roads, that are going to have to coordinate with each other, potentially to achieve global tasks such as rideshare or delivery. Also smart manufacturing, environmental monitoring, and search and rescue. So these are some of the application areas that motivate a lot of our thinking in this space. And so this problem is really at the intersection of robotics, control, and also communication, because that information piece is really important. And so kind of a bigger picture of how we address these different problems. First, we think a lot about resilient multi-robot coordination. And our specific direction that we look at, which Colleen also mentioned, is this idea of characterizing trust. Can we characterize the trustworthiness of other agents that we're collaborating with and the data that those agents are sharing with us? The other is sequential decision-making under uncertainty. So now if my agents have to make decisions over a longer horizon, how should we go about that? And that is mostly dealing with uncertainty, not necessarily the adversarial case. And there we look a lot at learning and the role that learning can play in supporting sequential decision-making. And the last piece, which is really kind of where we are now in our work in the lab, is to merge these two pieces of trust and decision-making. So can we kind of combine these two worlds? And so I'll mostly be talking about the first two pieces in my talk today. And one thing to mention is that communication and sensing is very much embedded on all of these directions. In fact, this is a common theme in our work, is that there's an interplay between the communication and the decision-making and the control. Okay, so I'll start by diving deeply into the resilient work that we've been doing, resilient decision-making and coordination. And so most of my talk today will be here in this area, and I'm happy to talk about other pieces as well. I'll highlight a little bit of our recent work in the sequential decision-making under uncertainty theme right at the end, towards the end of the talk. Okay, so to tell you a little bit more about this problem of coordination, I will just mention this classical result. So this is just to motivate the fact that multi-agent systems are vulnerable to information that could be malicious or adversarial. So a classic result is that in a consensus framework, agreement among agents cannot be attained if you have more than a certain number of malicious agents in the network. Either 1/2 of the network connectivity or 1/3 of the number of processors. And so this is a result that's well known. It's been studied. It's been studied even from a controls point of view. And it's a fundamental limitation. So then the question that we think of is, well, then what does that mean for when you put these systems out into the real world? It means that inherently they're pretty brittle and their coordination is brittle, and we have to think about how to strengthen that. And this is not just an academic exercise. The need to secure cyber-physical systems is on the radar of many agencies and institutions. For example, it's been named one of the NAE Grand Challenges, securing cyberspace. There's also been reports that are put out by the government and also reports to the president. So this was from the President's Council just last year, saying that there's a large need for cyber-physical resilience. And then this is not just in this country, this is across the world, the need to be able to secure cyber-physical systems. Okay, so throughout the talk, I'll use a few words. So I'll talk about the performance of a coordinated system or a multi-robot system. And what I mean by that is when multiple robots are working together, they're often trying to achieve some coordinated task. The degree to which they can achieve that task, I'm going to call it performance. And then the degree to which that performance can be maintained even in the face of an attack is what I'm going to refer to as the resilience of that system. And so what we look at is how can we categorize or characterize and also mitigate the impact of untrustworthy agents in the decision loop. And one example that I'll use throughout is the example of consensus, distributed consensus. And why consensus? Consensus is a core primitive to a lot of coordination tasks. And so a few examples are, for example, intersection management, autonomous vehicles going through a road network, federated learning, multi-robot mapping. Consensus shows up in a lot of different places. And it's also one place that can be very vulnerable to malicious agents or malicious information. So as one concrete example, I'll talk about platooning on a road network, just as a motivating example. So imagine here you have a case where agents must agree on their velocity or their heading in order to be able to merge successfully on a road network. So on the right, you see some schematic of what that might look like. So you have a few vehicles on a road network. Say they have a certain heading, they have a certain velocity. The velocity is shown by the magnitude of that black line. And this is what it would look like if they achieve agreement. And this is the average, say, the average of all of their heading directions. And this is what it might look like on the actual plot. If one of those agents is not able to achieve agreement, which is what you would see there, then that's a discrepancy. That's a discrepancy from the actual average that all of the agents are trying to attain. And it creates ruptures in the network. And so that's not good. So the deviation, which I'm calling delta, is something that we're interested in characterizing in the case of malicious agents or malicious action on the network, and also convergence rate. If I can converge still to a consensus, how quickly can I converge? So to talk a little bit more in depth about the consensus problem, first I'll formalize this. So we have a graph. and we have robots in that graph that we're going to call V. We have edges. An edge defines a set of neighbors, and we assume that each agent has some value x at time t. And what each agent is doing, if they're legitimate and they're following the protocol, is they're just updating their value by a weighted sum of all of its neighbors' values. And so those weights determine the influence that other agents have on each other's values. And here we assume we're in the synchronous setting, and we don't consider the availability of keys for security at this point. The reason for that is because we want to think of highly distributed, possibly highly heterogeneous systems where we might not be able to depend on a key passing system. And we also assume there's no centralized server. Okay, so an attack on consensus might look something like this. So if we have an attack on that heading direction, so we have a red agent that's denoted by the red line, that's a malicious agent input. The effect of malicious agents on the system could be various. It could various effects. It could be that they prevent the system from attaining convergence, or it could be that they break the formation, or many other problems like that. So here we have an example of a consensus system where we have multiple robots. Their communication ranges determine the neighborhood. And inside of this network, there's an adversary, a malicious agent. So they start off, they're trying to run consensus on heading as they're moving. And that plot that you see there, that's their heading values. And this is a scalar heading. So you can think of this as an angular heading value. And at the point where they're about to reach consensus, their network becomes particularly fragile, and the adversary decides to launch an attack exactly at that moment. And in this case, you see that the adversary can easily break the system. So it can break the network, and then this is a failure where agents cannot agree on a heading direction, and the team splits as a result. And so what we want to be able to understand in these cases are how can we quantify the performance degradation, so the divergence, or maybe bound the deviation of the malicious agents on the converged value. And we also want to know when this is happening, learn that this is happening, and then mitigate this occurrence if possible. So here's one example attack that we're interested in is a Sybil attack. So under a Sybil attack, you have a network that has malicious agents and legitimate agents. The legitimate agents follow the consensus protocol as we put it up on the slides a few slides ago. And the malicious agents do not follow the consensus protocol. And in fact, even moreover, they spawn identities in the network. And so here, all transmissions are synchronous. And then we assume that these sets L and M are static, but unknown. So on the left, you have a legitimate network. On the right, you have a network with Sybil entities. And that subgraph is a subgraph of malicious agents. And then Sybil attacks and location spoofing are two attacks that come up in various cyber-physical systems. So here are just a few examples of where they have been shown, where they come up in the news or in other academic articles about multi-robot systems. Okay, so how then, if this is such a pervasive problem, how is it approached so far in the literature? So I'm going to kind of compartmentalize these approaches into two broad categories. On one side, we have graph structure-based approaches. So these approaches use the idea or concept of redundancy in the network in order to cross-validate information and detect anomalies. And so there's been a lot of work. This is not exhaustive by any means, but there's been a lot of work in that area. On the other side, there are what I'm going to call physicality-based methods. So that means we have something additional in the network. For example, some infrastructure, some keys, some hardware that we can use to help secure the system. So first, I'm going to talk a little bit about graph structure-based methods. And so what graph structure-based methods are essentially you have enough redundancy, of enough connectivity in your network that you can actually still get legitimate information even if malicious agents make up some portion of your network. And those malicious agents can be anywhere in your network so long as they're limited in number. So that's the idea. And so long as you have a certain level of connectivity. And so this is what a resilient flocking would look like in the case of running resilient consensus, where now you have a graph structure-based method. So this was some work that we did where we used a control barrier function, and I saw that some of you guys presented control barrier functions in your lightning talks. So the idea here is to use a control barrier function around the communication network to be able to ensure that even as these agents are navigating through an environment with obstacles, they're always maintaining sufficient connectivity. And so you see that failure case of getting very close to being disconnected doesn't happen. So that even when the attack occurs, so here the malicious agent is actually attacking the consensus, the system is still able to reach consensus and maintain cohesion. Okay, so this is successful flocking. And in this paper that I mentioned here in the citation, what we looked at is under which conditions in the environment can we actually achieve this? Because you can imagine there's some conditions in the environment where that resilient network topology is not compatible with the navigation goals. Like you can get deadlock. And so we characterized what that looks like for this problem. So there are ways to approach this problem from a graph structure based approach, but I'm going to talk a little bit more now about the physicality based approaches, and I'll explain a little bit more what I mean. So one thing that we explore a bit in my lab and in our research is this idea of using the role of physicality, the fact that these robots are actually embodied, they're in an environment where they can share communication, they can share sensor information with each other. And the key question or the key idea here is, can we use the fact that we have all of these additional streams of information and sensing to be able to measure actually a quantification of trust? And if we can do that, then this can be very powerful for security and for securing these cyber-physical systems. And so this idea of being able to use sensing to actually quantify the reliability of a system is something that has been explored more and more recently. So there are ideas of, for example, location validation or watermarking signals. I would also be interested in talking to Chris. So some of Chris's some of the work that Chris presented, this is along the lines of what we're thinking. Agents that can sense their environment, perhaps see around corners, use that information to cross-validate. And the idea is to be able to quantify that and then use it. So here that idea is a little bit more formally. If we had additional information that we obtain from onboard sensors that can be mapped to some quantification, some alpha term, say between 0 and 1, that can characterize the likelihood that a particular transmission that an agent receives is trustworthy. So alpha closer to 0 means it's less trustworthy, alpha closer to 1 means it's more trustworthy. Then this might allow us to break past classical results in resilience. And that's what we want to achieve in order to get these multi-robot systems out into the real world. So this is a new model, and we call it a stochastic value of trust. So the question that we set out to answer at the beginning was, what if we had extra information in the network that we could exploit? Then would that help us on the control side of things, on the decision-making side of things? And so a little bit of terminology, we think of this quantitative measure of trust, alpha ij, as a way to limit the impact of malicious agents in the decision-making. So now if that's my network, instead of just relaying values xi or xj to each other, now each value also will have an alpha term. So an alpha value is communicated or measured really is what I should say, for every communication link in the network. And we need certain properties of these alpha values in order for them to be useful. And this here is maybe the mildest of these properties. And what this is saying is that in expectation, the values of these alphas, the expectation of these alpha values should be distinguishable from one another. Okay, so you can think of alpha as a random variable that has an expectation that's going to be different in the case of an attacking agent versus a legitimate agent. And so we will use this concept as an abstraction in our models. And so I will talk a little bit more about this, but I just want you guys to think about this now as an abstraction. And so really what we're after is this idea of quantitative trust. And you can think of this as being within the cybersecurity region, like the ball of cybersecurity, but a little bit more general than something like authentication. Okay, so you might be thinking, all right, that sounds like a good idea from a modeling perspective, but does this have any footing in reality? And so what I want to talk about is some experimental empirical evidence on what these alphas could be. But these alpha values are not limited to this. And in fact, I'll get back to that. Okay, so going back to the Sybil case, where you have one agent can masquerade as several unique but different identities. This is what it might look like in that case. So here we have the red cluster there are actual Sybil entities. So they don't exist. They're one physical adversary that's essentially spawning other identities in the system. If you have no way of measuring that this is happening, they look like unique identities. They all have unique IDs. They could have unique values. However, if you have a way to measure the fact that these are actually the same physical entity, that is what we would like to have as like the alpha value. And so here, what you see there, those plots are actually wireless fingerprints. So this is showing that if I had a way of sensing, say, a fingerprint over the wireless channel, I could actually tell that some of these agents are physically different than others, and the Sybil entities look very similar to each other. And in fact, we were able to show that you can measure such an alpha value from the wireless signals that has these properties on their expectation. And so that property will be important, and we'll use that again. And so this is what this looks like in an actual implementation. So here we have a Sybil attacker. It's spawning a cluster of malicious agents. And if you look at those wireless transmissions and you think of them as a fingerprint, and these are actual wireless fingerprints, you can see qualitatively that the agents or the fingerprints from different legitimate agents look quite distinct, whereas the Sybil entities on the right column look very similar. And this is what it looks like in a histogram form. So these are alpha values between 0 and 1 on the x-axis, and the histogram height is the frequency of receiving those alpha values. There are two things to note here. One is that these are actual measurements, so they're not perfect. They're stochastic. So you have sometimes you have misclassifications of legitimate agents that look malicious and vice versa. But in general, they do concentrate around these distinct expectations, these distinct average values. And so the main intuition here is that the alphas are drawn from a different distribution, depending on if you have a malicious transmission or a legitimate transmission. And these distributions are distinguishable from one another. So these are necessary criteria. Okay, so now that we talked a little bit about what these alpha values are and what their intuition is and their motivation is in the physical world, now I want to talk about how we're going to use them and how they're going to be helpful for us. So for the rest of the talk, I'm going to be using those alphas as an abstraction. So here's the idea. Going back to the consensus problem, each agent has a value x. And now what I want to be able to do is weight the input of the agents in a way such that those weights are a function of the alphas that I'm collecting, the observations. And so if I do that, then now the resilience of consensus can be characterized by understanding the properties of this sequence of observations, alpha. And then in order to understand that, I want to compare against the nominal resilience or the nominal consensus case, so with all legitimate agents. So you can think of, this is the case where if all of my agents are legitimate, the W bar is the ideal weight. I want to be able to compute the average consensus value. And so the error is what I'm going to call the difference between the nominal consensus dynamic, which would be the case with no malicious agents, and then the actual consensus dynamics, where now I'm using this weighted term. So this is the actual consensus dynamic by using the weights that are a function of alpha. And on the other hand, I have the true weighted average, what I'm trying to target. Okay, so I'm going to call that the error at time t. And importantly, there's also this t0. What that is it just allows me to observe the network and collect some alphas for some amount of time t0 before I start my consensus. And then all the results are going to be stated in terms of t0, but this is arbitrary, so we can make the choice of what t0 is. Okay, so here's the problem then. I want to be able to find a weight matrix W. I want to find a definition for this weight matrix that's a function of the T0, such that for any given failure probability that I choose, delta, I can bound the probability that my error is outside of some theta max, some delta max within some failure probability, okay? So I can't guarantee that my deviation will be within a certain amount, but I can say with high probability it will be, and that's what I'm after. Okay, so what does that look like schematically? If you look at the schematic on the right, the true average is shown in black, the actual consensus dynamics are shown in green, and the malicious agent input is shown in red. If I do not use a resilient weight choice, then this is what would happen. All legitimate agents would converge to the malicious agent input. And my delta would be very large, the deviation from my true consensus that I'm trying to go to. What we're looking for is a definition of those weights such that the deviation from the true average can be bounded, and ideally can be small as possible. Okay, so how are we actually going to do that? The way that we do that is that we define the weights as a function of this sequence of alphas. So think of taking a sum of all the alpha observations that I've gotten up until time t. And then I'm using that, I'm going to call that beta, and I'm shifting it by a half so that intuitively malicious agents should have betas that are growing towards negative infinity, getting more and more negative. And legitimate agents should have alpha values or beta values that are becoming more and more positive. So this is what a legitimate agent sequence of betas might look like over time. And this is what a malicious agent sequence of betas might look like over time. And then I'm going to use that to define a trusted neighborhood. So I'm going to say that if my beta value for a particular link is greater than 0, then I trust this agent. And if it's not, then I don't trust this agent and I assign them a weight of 0. So this leads us to a new weight definition, which is exactly that. If I trust an agent, I'm going to take 1 over the number of trusted neighbors that I have, and those are the weights that I'm going to assign to everybody. If I don't trust an agent, I'm going to give them a weight of 0. And so what you see in a plot or schematic form is on the y-axis, I have weights, and I'm looking at those weights over time. So for the legitimate case, it might look something like this. Sometimes I classify it correctly, sometimes I classify it incorrectly. So I think a legitimate agent is malicious and vice versa. But what we would expect is that over time, I will converge to the true nominal weight of that agent if it's legitimate, and similarly if it's malicious. So that's the intuition of what we're targeting. And this is a result that says, indeed, this will be the case. And so here is an important and kind of critical lemma in this whole analysis. which basically says that the probability of a misclassification is decaying exponentially in the number of observations that I get. And that's basically what this is showing here. So it's misclassification of an agent as malicious when it's actually legitimate, and vice versa. And I'm not going to go through the details of this, but I'll mention that this relies on Chernoff-Hofting inequality. And basically it goes back to the fact that we know that each of those alphas has an expectation that's bounded such that they are different. Malicious agents are bounded near 0 in expectation, and legitimate agents are bounded near 1 in expectation. And so an important corollary of being able to do this, of being able to show that this misclassification error decays exponentially, is that the misclassifications should occur finitely often in the limit. So there should be a time in which I can say, after this time, I will have no more misclassifications. So I will have learned who I can trust and who I can't trust. And so this is the time that we call TF, and we showed that such a time exists. Now, an important point to note here is that that TF is finite, but it's stochastic. So we don't know when it will happen, and there's no way of agents checking if this has happened yet. We just know that it will happen in the limit. And of course, we're interested in how quickly we get there, but that's another point which I will leave till later. But this establishes an important result. And this result says that if I use this resilient definition of weights based on these alpha observations, then I can achieve distributed consensus, even in the case where the number of malicious agents is more than 1/2 of the network connectivity. In fact, this is independent of the number of malicious agents in the network. So that's really important because that allows us to start breaking past some of the classical results in resilience that limit the number of malicious agents you can have in the network. So that's the first thing. The other thing is that the deviation, how far you are when you converge from the true average, that is still something that exists. So there is going to be a deviation, there is going to be a penalty for malicious agents existing in your network, but this is something that you can characterize. Okay, so this is what it looks like in a numerical studies point. So in this numerical study, agents are trying to reach a consensus on who is trustworthy and who is not. Here we have two different types of graphs, one more connected than the other. And you can see that they both converge, they just converge at different rates. And so that's what you see. And one thing I'll point out is that the number of legitimate agents in this simulation is 80, and the number of malicious agents is 120. So far beyond half of the network. Okay, so from here, we wanted to explore many more problems in this domain, and I won't have a time to go through all of them, but I wanted to highlight maybe a few. So we really started having fun with this problem and asking many more questions, like, for example, what happens in the time-varying attack case? Or what happens in different network topologies, like directed graph case? So I'll say a few words about the time-varying case. So I want to revisit one of the assumptions. So one of the assumptions in the work that I just presented was that malicious agents will always be malicious and legitimate agents will always be legitimate. And so if that is true, if malicious agents are always malicious and vice versa, you would get a beta sequence that looks similar to what I showed before. In the green is the case of a legitimate agent, in the red is the case of a malicious agent. But now, if my malicious agent can attack sometimes and not attack sometimes, it starts to get a lot hairier. And so, for example, if, say that this is the case of my legitimate agent, they're always legitimate. And this is the case of the malicious agent who's always malicious. So these are the two extremes. And in that case, I can very easily pick a classification threshold to determine which is which. But now, if my malicious agent has an attack probability of 1/2, so half of the time it's attacking, half of the time it's not, its beta sequence will look different. For example, something like what I just drew. Or if their attack probability is 20%, so they attack less often, they start to look more and more like my legitimate agents. And so the ability to distinguish between them, and in particular find a threshold of classification between them, becomes more and more difficult. And so depending on the attack probability, you can be anywhere in this cone. And so clearly the classification problem becomes harder. And the question of the classification threshold that I should use is a big research question. And so this is the topic of a recent paper that we just published last year in CDC, and we are still actively publishing in this direction. So this is still a direction of research for us. But I can just give you a little bit of an answer on this. So we do find conditions on the attack rate, and also a few other conditions on the threshold to show that we can still achieve almost sure convergence in the limit, even for the time varying case. Okay, and then we also looked at the problem of directed graphs. That's a really important problem. I'm not going to go into it right now, but I'll just put a pointer there that we have a paper that was published in L4DC in 2023, and also a paper that's under review right now in that direction. Okay, so kind of I want to pop up and give a little bit of a bird's eye view of the work that we've done in this space to give a flavor of how kind of versatile this idea is. So we've looked a lot at the resilient distributed consensus case, and we've looked at convergence results, rate of convergence results, different graph topologies, and time varying attacks. We've looked at the resilient distributed optimization case. We've characterized convergence and convergence rate for those. And we've looked at the resilient hypothesis testing case as well. And these problems all use the same idea, that if we have stochastic trust observations, or these alpha values, for weighting the inputs from different agents in my network, then this leads to provable resilience. And so I'll talk a little bit more about the distributed optimization case now. So in that case, we assume that we have a sum over different functions where every agent has its own function fi. And our goal is to achieve fast convergence to the optimal point x star, the optimal point being the global optimum there. And so we have several assumptions. For example, we assume that these functions are strongly convex. We assume their gradients are Lipschitz. And then we have a constraint set that we allow, but we have restrictions on. And then again, we have access to these alpha values. And the alpha values have the same assumptions as before. And the graph is sufficiently connected. So that means if I remove the malicious agents, then my graph over legitimate agents should still be connected. And so if I look at the iterates for my distributed optimization, and this, by the way, is vanilla distributed optimization, even in a case where you don't have malicious agents, I want to explain a little bit about what's happening here. So in the distributed optimization literature, if agents can estimate a gradient and then use that estimated gradient in their update values, what you're doing is you're essentially having a consensus step and an optimization step in sequence. And so this was work that has already showed that this additional gradient information allows for fast convergence. So that's really good from a distributed optimization point of view. However, if you add malicious agents into the mix here, this allows for new attack surfaces because essentially your malicious agents can lie about those gradients. And that becomes very problematic for the distributed optimization case. And so basically they can drive the optimization point to anywhere in the space by manipulating the gradients. And so the question that we ask here is, can we use this concept of trust and gradient tracking so that we can still converge quickly, but converge to the right optima instead of actually instead of allowing the malicious agents to drive that value anywhere. And so here we're going to use the same idea of incorporating trusted neighborhoods. So remember, we're going to use that beta value, and if it's greater than 0, I'm going to declare that as a trusted neighborhood. And we want to derive sets over which we can project such that we can contain the malicious agent's influence as we're learning their identity. So that's kind of the key intuition here. And so what this looks like is this modified distributed optimization will now look like the following. So instead of just doing gradient estimation, I now add a projection. I'm going to project onto some set S, and then I'm going to update my iterates. So I still have a consensus value-based update, but then I have an additional projection step. The idea of these projections is to essentially limit the impact of malicious agents, because I recognize that there are some agents in my network who are not trustworthy. And there's going to be some time that the algorithm will need to be able to learn who is trustworthy and who is not. And here you just have step sizes like you would in the normal vanilla version of the distributed optimization. So the key question here is very similar to the consensus problem, but now we're trying to learn the R matrix and the C matrix, which are essentially the mixing matrices of how I'm going to use information from my neighbors to update my iterates. And I'm using, again, the trusted neighborhoods here. And so the idea is that I'm also going to learn these sets, this Z set and the C set. So, the Z set and the S set. So basically what this is, it's saying that I want to project, there's the two projections. I want to project in order to maintain or mitigate the influence of malicious agents as I'm learning. And the key idea in this paper, which I include the citation for there, is to define how those sets should grow over time such that I achieve two things. One is that I mitigate or limit the impact of malicious agents as I'm learning whether they're trustworthy or not. And two, after a certain amount of time that we know exists, because we have the TF, which means there's some finite time over which I will learn who I can trust and who I can't. At that time, I can actually recover the optimal operation of my distributed optimization. And so then that's basically what this result here shows, which I will just say somewhat informally and give a pointer to the paper for the more detailed explanation. But the idea here is that we can actually still converge, and we can maintain a geometric convergence rate, which was the original convergence rate of distributed optimization, even with malicious agents in the network. And importantly, different from the consensus work, because here we do have a gradient and we're estimating the gradient over time, we can recover the deviation. So we can actually converge to the true optimal. And so this paper, this is brand new work. Actually, it hasn't even been published yet, but I wanted to show it to you guys so that you could see kind of where we're heading with this work. And so here's what it looks like in simulation. So this is the setup. We have the particular function that each of these agents are running is what you see up there. And we have a certain number of legitimate agents. We have 50 legitimate agents and 100 malicious agents. And on the right here, you see the graph of the deviation from the optimal, the actual optimal value. And so what I'll point out is the first work that I showed with just the consensus, because you can write a consensus problem as a distributed optimization problem. That's what you see with the blue arrow there, because in that work, we knew we would have a deviation that we could never recover from. But now, if we pose that as a distributed optimization problem, then when we run this new algorithm, which is the resilient push-pull algorithm, we can actually get rid of that deviation. So this is going to 0, and we can do that much, much faster. So this was one work that I wanted to point out, even though it hasn't been published yet. So these are new results, but I wanted to share them with you and maybe chat about them later. Okay, so I will talk a little bit about the resilience hypothesis testing work that we've done, more just to show you what this might look like in a practical setting. So this problem is motivated by a traffic estimation problem. So here we have multiple, say, cars on a road network, and each of these cars are transmitting a bit of information about whether that segment of the road is congested or not. So everyone's sending some bit to a fusion center, and the fusion center has to put this information together into a global map. So this is inspired by systems such as Waze, where there's some crowdsourced information of a map. And so here we have a binary event detection. So if the road is congested or not, this is the essentially binary event that we're tracking. And then different robots send their measurements to a fusion center, and they also have some error in their reported value. So it is possible for a legitimate agent to be wrong and send the wrong information. And robots can be either legitimate or malicious. And then importantly, malicious robots can lie about the state of that segment of the road. So their goal might be to switch the decision at the fusion center of whether a road is congested or not. And so this is an actual experiment in our lab. We have a mock-up road network where we have legitimate agents. So these are physical agents that are navigating on the road. And these are malicious agents. And each malicious agent can spawn Sybil identities. So that's what you see as these faded robots. Those are actual Sybil agents. They're not real. But they are sending values to the fusion center just like any of these other agents. And the difference here is that the fusion center is also measuring the signatures, the wireless signatures over each of the links. So every transmission, the fusion center is also estimating the fingerprint or the similarity metric in this case, which is the alpha. And this is what it looks like in practice. So you can see that Sybil identities have very similar fingerprints, whereas physically legitimate agents have very different fingerprints. And so this is what those alpha values look like in the actual experiment. So you see that for the legitimate agent case, those alpha values are very close to 1. And for the malicious agent case, those alpha values are very close to 0. So you can think of this as a similarity metric of the wireless transmissions that are sent to the fusion center. And so in the actual experiment, what you see here are agents navigating over the different road segments. In the large panel, that's the ground truth of whether a segment is actually congested or not. Congested means 2 or more physical robots are on the same road network. And in the upper right, you see the different algorithms. There's the oblivious case where the fusion center does not have the alpha values, and then the other 2 algorithms that use the alpha values. And in the plot, you can see that the probability of error of the fusion center is much lower for the case where we do use this additional information coming from the alpha values. Okay, so just a quick summary of this idea of stochastic trust. So this is a general framework. Wireless channels are one example of where you can measure alpha values. However, finding more is an open problem. And from the theory, we can already see that it's very worthwhile to be able to use physicality to get a broader understanding. And importantly, these should be distinct under different attack conditions. And these alpha values and this idea of quantitative trust provides a bridge between theory and practice. So in the last 5 minutes or so of my talk, I'll talk very quickly about some of the work that we've been doing on the case where data might be trustworthy actually, but it could be incomplete because there's just a lot unknown in real world environments. So like John was mentioning over lunch, you don't have a God, when you go out into the real world, like a motion capture system, right? So there's a lot that we don't know. So for these problems, we look at a framework of sequential decision-making that uses a rollout-based reinforcement learning methodology. And so here we have some look ahead that we're using to estimate the current cost, and then we're estimating the future cost by using a base policy. And that base policy could be heuristic based on some kind of a known model, or it can be learned from data. And so we've applied this in many different contexts. We've looked at routing problems where you have imperfect knowledge about where future demands might be coming up, but you have to deploy a fleet of agents to go satisfy those demands in the environment. We've looked at the stability of the learned policy, whether or not the learned policy will be stable. And then we've also looked at decision-making in highly partially observable settings. And so I'll talk a little bit about our most recent work in that direction. So in that direction, the problem here is we want to be able to do sequential decision-making in a way that's adaptive to information that we get on the fly. And so this is necessary for highly dynamic and observable and partially observable settings. So the problem that we use here and the problem that motivates this work, so in application, is a problem of whale rendezvous, actually. So here we have whales that can surface. They surface for only 10 minutes every hour, and we want to deploy a set of robotic agents to rendezvous with them visually rendezvous with whales whenever they surface. And so there are important few things to note. One, there's a time criticality aspect. The whales are only up for 10 minutes. It's partially observable because when the whales are underwater, you don't know where they are, but you do get acoustic vocalization information, which I'll talk about a little bit more. And then there's a discrete and continuous space here because the whales could be anywhere, but they're either at the surface or they're not. So they're either available for rendezvous or they're not. And so we base a lot of this work on rollout with partial observability, so that this is work that we've done in the past with some collaborators like Dimitri Bertsekas. And we combine this with in situ sensing. So we developed a robot, a drone that has a sensing payload on board, and it can sense angle of arrival to very high frequency pings that come off of a tag if the whale is tagged. The whale is not always tagged, and in that case, we use acoustic-based localization. So what that means is when they're underwater, they vocalize, and there are acoustic sensors that can provide angle of arrival to their vocalizations. And so the idea is to use on the left a lot of the sensing that we get in real time and plug that into the decision-making algorithm. And on the right, what you see there is understanding how to predict the future, predict when they might be coming up and where they might be coming up in order to be able to route your drones to be able to rendezvous with them most effectively. And so we derived a whole framework for that, both the system development, the sensing system on the drone, as well as the decision-making system that's doing the routing of the drones to rendezvous with the whales. And that was a recent publication for us last year. And this is a video just showing you kind of our most recent updates on this work. So this is in Dominica. There's a catamaran with an acoustic towed array that's in the water. So that towed array is picking up angle of arrival to whale vocalizations when they're underwater. And there's an autonomy module, which is essentially doing all of the decision making on board and sending commands to a drone. So the drone, the objective of the drone is to be able to fly and rendezvous with the whales when they're about to come up. So this is my student Ninad, and he deployed the drone. And then now the drone is essentially getting information from the autonomy module that's on the catamaran, that's listening to the acoustic vocalizations of the whales underwater, and is essentially computing a belief and also a routing strategy for the drone. And it's communicating that information to the drone, and the drone is flying in an attempt to rendezvous with the whales. And this also kind of gives you an appreciation for how difficult this problem is, because the ocean is very vast. And even though the whales are large, it's very hard to actually understand where they are. It's very noisy information. We don't have GPS. These whales are actually not tagged at all. And we're not using vision here. In the future, we will use vision most likely, but right now it's just acoustic. So, so this was actually the first time that we were able to achieve real-time rendezvous with the whales and the drone flying completely autonomously. And that red arrow is what you see. That's the closest that we were able to get to the whales autonomously. And then we took over manually to get right on top of the whales and have a ground truth of their actual position. Okay. So with that, I'll wrap up. So a lot of the work that we do is characterized by this interplay of using controlled mobility and information exchange. So there's very much a kind of a closed loop between the decision-making and the information. And also, my group looks a lot at the theory side, but also the practice. So we look a lot at how do we get things from from the lab into real world environments. And so we had a few experiments like the adversarial hypothesis testing experiment. We have an ongoing collaboration with the Harvard Evening Van at Harvard, which does a lot of our routing. We get a lot of our routing data from there. And then we also have our ongoing project with studying whales in Dominica. Okay, so I'll just pose a few open questions that we're still investigating. One of them is the question of dealing with strategic malicious agents, the case where agents can attack or not attack in a strategic manner. That's something that has proven to be quite difficult, and we're still looking at that. The other one is heterogeneous networks. For example, if we use this concept of learning trust, and some agents in the network are inherently more trustworthy than others, how do we deal with that heterogeneity, or even how can we exploit that heterogeneity? And then the third one is more examples of quantification of trust that can be measured from physical signals. And on that topic of physicality-based trust, I'll talk a little bit more. So we showed that using the wireless signals of the communication is one way to extract these alpha values. But this question of what other physical sensing mechanisms we can use to observe and quantify trust is still underexplored. And we're actually working on a survey on this topic. And I'd be happy to talk to some of you in the audience also. So in conclusion, our multi-agent cyber-physical systems bring a lot of new opportunities to the table. But they also have new challenges as we put them out into the real world. For example, dealing with malicious agents or malicious data, dealing with dynamic networks or heterogeneous networks. And so formalizing a notion of trust allows for new mathematical models that then upon which we can build more resilient coordination algorithms, which is what we would like to do. And so here are a few acknowledgements. We have a lot of collaborators that we've worked with very closely on this, and I've highlighted a few of them, like Angelia Nadich, Michal Yemeni, Andrea Goldsmith, and also students in my group. I've highlighted the names of the students that contributed mostly to the works that I talked about today. I'm really lucky to work with a group of very brilliant students. And then last thing I'll do is mention that we are organizing a workshop on multi-agent, multi-robot systems at the upcoming RSS. And I saw many of your presentations already. It would be amazing to have some of you participate in our workshop also. So there's a link. We are accepting contributions, and we will be selecting a best paper and a best poster. So that will be on July 25th at the upcoming RSS. So hope to see you all there. And with that, I will just take questions.
Stefan, very nice talk. But I don't know if you know, but we have done a tremendous amount of work on trust.
Again?
We have done a tremendous amount of work on trust,
Yeah.
including trust for collaboration based on actual measurements. Actually, one of the best students was Xiangyan Liu, who's now very high up in Google. So, and we actually have improved. I think we have the best number of attacks you can have, but we did it a little bit differently. Each agent collects data from others and estimates trust value for the agent.
Yeah.
Then if the trust value falls below a threshold, you're excluded from the consensus. So the problem was how many you can tolerate, what are the conditions you want to estimate to improve, and then what is the remaining connectivity, right? So we have several patterns of that, but that's old. It's about 10 years old. But anyway, I don't know if you know this work. And then we did a lot of work on physical layer of authentication, what you call physicality.
Yeah.
So we used channeled information with Johnny Tao, who started a company on that.
Yeah.
So I don't know how much of that has penetrated your circles because I don't see any reference. So the big question I have in my mind is human factors, because we apply this to social networks, trying to understand the problem everybody tries to understand, how I can stop propagation of misinformation by trustworthy and untrustworthy. And we had several values of crowdsourcing and kind of algorithms on that. So have you tried to do any of that on social networks or cyber human physical systems where, in addition to the physical and what I call the P part, you've heard me ask people in CPS, if you do cyber physical security, where's the P, which you're using in your physicality? But then you have human behavior.
Yeah.
So, and then it becomes more complicated because in addition to whatever else you have to decide yourself or what is your attribute? Are you a person who trusts easy or don't trust easy? Some of the alpha things you mentioned may be more useful there than actually physical measurements.
Yeah, that's a really great question. So we've started thinking about the human aspect and if we can translate some of these ideas to human robot interfaces. We haven't gone very far in that direction yet. So as of right now, we're operating under the assumption that we can measure some alpha value. So we need something quantitative. I think it's possible to do this with humans too. We just don't know what those alpha values would look like for that case. Right. Yes.
So one of the things we proved is that
Yeah.
if your trust algorithm does not converge faster, for instance, you go to the original problem.
Yes.
If your trust algorithm does, as you have dynamic environments, which you mentioned briefly, I don't know if you've done any work in dynamic environments, but the trust is dynamic quantity. And if the trust values do not converge faster
Yes.
than the dynamics of the consensus, you are lost.
Yes, definitely. That's definitely true. Yeah, so right now we're like knee deep in thinking about the dynamic case. Yeah,
To get different, the combined metric.
yeah,
Trust any of the agents or not.
yeah.
And,
Yeah.
then
Yes. Yeah, in all of the work that I presented today, we assume you have sufficient connectivity, which essentially kind of basically brushes that problem under the rug, because if you don't have that, then there's nothing you can do. Yeah,
and with the connectivity.
yes.
So
Yeah, I think I would definitely want to get some paper pointers from you. I know that we've talked a bit about this, so I'm gonna pick your brain a lot more after this. That'd be great. Yeah, 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 yeah. Yeah, this would be great because we're actually working on a much broader survey paper right now on quantitative trust. So I'd very much like to talk about that and maybe get some of these into our survey paper.
Question?
I was interested in your final project, tracking the whales, and I was wondering if you had given any thought to either detecting or dealing with the potential for avoidance behavior based on either your attempts to track them or some sort of outside human activity that was going on, you know, and then of course that could apply to if you replace the whales with, say, like an adversary submarine or something like that.
It's a very good question. Yeah, so actually, so that project is just a sub piece of a much larger project. The objective of the project overall, which is multi-university, multi-country actually, is to decode whale communication. And part of what we need to acquire to really get at that question is getting the full contextual information. So for example, how do whales react to our attempts to study them or to other boats or other fishermen or other tourists that do swim with the whale activity? So we're in the process of trying to map all of that kind of bigger picture, but right now we don't track that yet.
I recognized a few names on the paper and thought it might be.
Yeah, yeah. Thanks, Colin. I'm happy to take more questions later.